Amazingly, although these striking similarities were staring the geologists in the face, they never put two and two together. Of course, as far as the lunar geologists were concerned, the Earth and Moon must have shared the same origin.
Perhaps these strident similarities between Earth rocks and Moon rocks were overshadowed by the even more obvious differences in their chemical composition and mineralogy. For instance, some of the most common minerals found on Earth are completely or nearly absent in Moon rocks. Quartz.
Quartz? Quartz? Are you kidding me? So far he's only listed one example, and already his logical fallacies are off the chart. The Apollo samples are generally either basalts or gabbros, both of which are solidified pieces of lava, breccias, which are composed of fragments of stones, in this case volcanic stones, or anorthosites, volcanic rocks that are mostly or completely made of plagioclase. Quartz is a mineral common to the Earth's crust and its beaches, not to the basaltic rocks from the mantle. One of the most common questions that you'll get asked in a simple geology test is, what minerals do you expect to find in a basalt? And the correct answer is olivine, pyroxene, and plagioclase. And what do you know? These three minerals have been found within the same ranges in both terrestrial basalts and Apollo samples. All that really needs to be said is that Webb is clearly comparing apples to oranges again, this time by comparing the Apollo samples with rocks from the Earth's crust, rather than its mantle. But it seems that Webb is also guilty of a fallacy of omission. You see, although terrestrial basalts generally contain plagioclase, olivine and pyroxene as primary minerals, there are known exceptions in which they contain significant amounts of quartz. As you'll learn in a basic geology test, this is typically because magma interacted with sand or rocks surrounding the magma chamber. Likewise, there are many notable examples of quartz-rich Apollo samples, such as Apollo sample 12013, which is 22% quartz. And who could forget sample 14321, or Big Bertha as the press calls it. One of the large clasts, or fragments found in this 9-kilogram rock, is 40% quartz. And then there are many pigeonite basalts from Apollo 15. All of these basalts contain quartz as a normative mineral, meaning that they contain huge amounts of quartz. On page 33 of their book, Mason and Melson display the following table. It covers the minerals of the Apollo 11 samples and divides them into three groups. Major minerals, minerals that are in excess of 10% by weight, minor minerals, which are minerals that range between 1% and 10% by weight, and accessory minerals, minerals that are less than 1% by weight. I must stress that this table covers only the Apollo 11 rocks, not the various quartz-rich rocks from the later missions. Looking at this chart, we find that there are three types of SiO2 found in the Apollo samples, quartz being one of them. The other two forms of SiO2 found in Apollo samples are cristobalite and tridymite, both of which are polymorphs of quartz. Now, because quartz falls under the category of accessory minerals, Webb can presumably come back with, "Oh, there's very little quartz in the Apollo 11 rocks." If that's what he comes back with, he'd better be ready to offer reconciliation for his original claims, because later in his video on the Dutch moon rock incident, he claims that there was no quartz at all in the Apollo 11 samples.
Nothing resembling the Drace rock is in the Apollo 11 sample catalog or the Lunar Sample Compendium. The Drace rock is closest in weight to sample 10022, a basalt rock. The Drace rock is quartz, and there are no quartz stones listed among the Apollo 11 samples. There were 19 basalts, 30 breccias, and a 1-pound gabbro, but no quartz.
But there is quartz in the Apollo 11 samples. Even if Webb was to come back and say that it was one of the minerals that are nearly, not completely absent in the Apollo samples, this demonstrates selective cherry-picking on his part. In this case, by focusing only on the Apollo 11 samples with very little quartz in them and ignoring the many oversaturated rocks from the later missions. The other minerals that Webb claims are absent in the Apollo samples are calcite, magnetite, mica, amphiboles,
and sulfide minerals, pyrite to be exact. As with quartz, calcite and pyrite are both minerals common to the Earth's crust, not the mantle. For this reason, terrestrial volcanic rocks like basalts and gabbros also tend to lack calcite and pyrite. This is more apples and oranges. As for the other three minerals, it is incorrect to say that they do not exist in the Apollo samples. Magnetite, mica, and an amphibole mineral were all discovered in the Apollo 11 samples as early as 1970 by Gay, Bancroft and Bown of the University of Cambridge. This is discussed in their study titled Diffraction and Moss-Bauer Studies of Minerals from Lunar Soils and Rocks. While they didn't mention calcite, a calcium carbonate, they did find its brother, aragonite. And whilst we're on the subject of amphiboles, it should also be pointed out that analysis of various high titanium Apollo 11 samples led scientists to believe that they were derived from the melting of amphibole minerals, and thus the lunar mantle is rich in such minerals. Mason and Melson write about this on page 153 of their book.
Another intriguing possibility is that the titanium-rich basalts on the Moon may have been derived from the partial melting of an amphibole peridotite, a rock type which O'Hara and company have suggested as a possible material for the Moon's interior. Amphibole is a rock-forming silicate with a capability for marked titanium concentration. The variety carcitite can contain up to 10% titanium oxide. The Apollo 11 samples can be fairly closely matched with terrestrial carcitites, as can be seen in the following comparison.
I think it goes without saying that, aside from sodium and potassium, Apollo sample 10084 and terrestrial carcitites are almost exactly the same. In fact, this very same sample in question, believed to be a melted amphibole, also contains the sulfide minerals that Webb claims are absent in the Apollo samples. In the 1970s science article, Search for Magnetite in Lunar Rocks and Finds,
several free opaque or half-opaque minerals were found: ilmenite, sulfides, metallic iron, hematite, and goethite.
Far from being completely absent in the Apollo samples, 5 out of the 6 minerals listed do in fact exist in these rocks. In the case of the odd one out, its sister mineral was present. And even if the minerals quartz, micas, and sulfides were absent in these stones, it would be completely irrelevant, because anyone who's passed high school geology wouldn't necessarily expect to find the said minerals in igneous rocks to begin with. These are minerals common to sedimentary rocks. But is Webb really to blame for this irrelevant argument? Reading through Webb's bibliography, we find a link to Randy L. Koratev's Washington University article, How Do We Know It's a Rock from the Moon? This site seems to be Webb's primary source of information, as in parts he parroted it word for word, or at least almost word for word, because a closer inspection of Webb's source material reveals that he either didn't understand the information he plagiarized, or deceptively tried to change the scope by destroying the exception. For example, Koratev states,
some of the most common minerals at the surface of the Earth are rare or have never been found in lunar samples. These include quartz, calcite, magnetite, hematite, micas, amphiboles, and most sulfide minerals.
Now where have I heard that before? It is important to note that Koratev explicitly states that these minerals are common to the Earth's surface. From this alone, we don't need to second guess that he is referring to rocks from the Earth's crust, not the mantle. But Webb changes scope by substituting most common minerals found at the surface of the Earth with
some of the most common minerals found on Earth are completely or nearly absent in moon rocks.
This deceptively combines the logical fallacies of destroying the exception and changing scope, by applying the characteristics of rocks from the Earth's crust to Earth rocks in general. Now as for Koratev, the only thing new here is that Koratev adds hematite to his list of supposedly absent minerals. This is also wrong. It was discovered in the Apollo 11 samples by Ramdor and El Ghazi. This was published in their science article, Opaque Minerals of Lunar Rocks and Dust from Mare Tranquillitatis.
Hematite occurs as fine lamella within a few ilmenite grains in the shocked breccias. The optical identification of hematite was confirmed by microphobe analyses.
And let's not forget the samples that show heavy signs of hematite, such as sample 66095, which is riddled inside and out with ferric iron oxides. Getting back to the subject of quartz, Korotev repeatedly brings our attention to it a few times in this article.
A rock that contains quartz, calcite, or mica as a primary mineral is not from the moon.
A more accurate statement would be, a rock that contains quartz, calcite, or mica as a primary mineral might not be from the moon or the Earth's mantle. Because although both typically contain mostly plagioclase, olivine, and pyroxene, there are exceptions in which they are primarily quartz. Fortunately, unlike Webb, Korotev later specifies that he's comparing the Apollo samples to rocks from the Earth's crust, rather than its mantle.
As noted above, lunar rocks don't contain carbonate minerals or abundant quartz, as do most terrestrial sedimentary rocks.
A sedimentary rock is a rock that was formed at sea level. But the Apollo samples and terrestrial basalts are both igneous rocks, meaning that they formed from the solidification of magma. I don't know if Webb knows the difference between the two types of rock, but he later uses the term igneous rocks in his series.
It would take more than simply scraping fragments from one of Apollo's moon rocks to create something that could pass for the regolith samples brought back by Luna 16. Notice the abundance of those tiny watery glass spherules in the right-hand picture? Those wouldn't just drop out of the igneous rock that Jarrah shows in the left-hand picture. Actually, I'm surprised that Jarrah put these two pictures together to begin with.
If Webb is truly as intelligent as he claims to be, he must therefore know the definition of the term igneous rock. Likewise, he must know the difference between lunar igneous rocks and terrestrial sedimentary rocks, and therefore, he knows that Korotev is only talking about the differences between these two types of rock alone. Therefore, he knows he is comparing apples to oranges when he applies the characteristics of terrestrial sedimentary rocks to terrestrial rocks in general. Webb is either incredibly ignorant or a bad liar. I'll leave you to decide which. It may very well be useful to distinguish terrestrial sedimentary rock from, quote, lunar igneous rocks and explain why they are different. After all, 3/4 of the Earth's surface is sedimentary rock. But it is equally important to compare terrestrial igneous rocks with lunar igneous rocks and show why they are the same. Otherwise, the comparison is just apples and oranges. And that's pretty much what this entire article is, apples and oranges. Other than a couple passing mentions, Korotev totally avoids mention of terrestrial igneous rocks and compares the lunar samples to terrestrial sedimentary rocks. He also ignores eucrites and compares the Apollo samples to chondrites, stony meteorites that contain round grains called chondrules, and vastly different chemistry and mineralogy to the Apollo samples. Yes, it is important to discuss why chondrites are different to the Apollo samples, but again, it will only be apples and oranges if the non-lunar meteorites that are similar to the Apollo rocks are excluded from these comparisons.